Okay, so far we've looked at capacitive reactance, and remember how did we define reactance? It was the opposition to current flow, so pretty much the same as resistance is. However, it's determined not by just the resistor or anything like that, but by the frequency of the signal that is going into the capacitive circuit. Okay? Inductive reactance is the same, but instead of obviously being a capacitor, it's now with an inductor. So all an inductor is a piece of wire. Even a piece of wire on its own has some inductance. Any current, any coil or any conductor carrying current will exhibit inductance, and that's because of something called Faraday's law, which Faraday's law is something that Michael Faraday found, is where a coil carrying or a conductor carrying a current produces a magnetic field around it. Okay, so I think actually next week I'm going to demonstrate that principle with, we've got some magnets and coils and things like that on a board set up. So I'll show Lenz's law and Faraday's law next Wednesday. So all we need to know is that an inductor is something that can store energy in the same way that a capacitor can stores energy, but instead of being an electric field like a capacitor does, it stores it in a magnetic field. If I had a coil like this with a current flowing through it like this, we would end up with a magnetic field being produced in that coil. Okay, so it'd be an electromagnet. So all magnets that they're like, you see at the metal recycling shop, they lift up a car body that's been crushed into a cube, right? They picked it up with a big magnet. That's an electromagnet. What they do is they have a big coil inside there, and they just pass a current through it, all in one direction, and it creates a magnetic field around that coil. Okay. If though I were to change that current, so if I have a changing current, I get a changing magnetic field. Okay. Okay, so that's important. If I have a current flowing through a coil, I get a magnetic field around it. If I change that current, I'm going to get a changing magnetic field. Incidentally, a changing magnetic field induces a current in a conductor near it. Okay, so if I, just ignoring the fact we've got a current through there now, if I had a magnetic field and I started to change that magnetic field, let's say I had an actual permanent magnet next to this coil, and I move the permanent magnet away from it, it's going to change the magnetic field that's actually in that coil. Okay, which will induce, that changing magnetic field will induce a current in that coil. Now if I happen to change that magnetic field in such a way that it produces a current in, let's say, in the direction I've shown it on this picture, then I can say, okay, that current there is going to be induced by that changing magnetic field. If I have a changing current, I get a changing magnetic field. That changing magnetic field induces a current in the same direction as the current is currently flowing. Okay, so that's Lenz's law. We get, so let's say I have my current here and it is increasing. So this is current over time and it's increasing over time. Then that magnetic field here will be increasing, and let's say it's increasing with this being north. Okay, so this is north and it's getting stronger and stronger and stronger north. Okay, but that changing magnetic field there will actually be trying to induce a current that's going in this direction. So this is the induced current is going to be in the opposite direction to the current that is currently going through it and increasing. Okay? And that's going to have the effect of trying to stop that increasing current. Okay? So a good way of thinking about it is, if I have an inductor with a constant current flowing through it, so we call that a DC current, so it's continuous current, it's not changing, then that inductor is happiest. The magnetic field isn't changing, and so there's no change in magnetic field to try and oppose or induce a current in the coil. If, however, I start to either increase or decrease that current, it changes this magnetic field, which will cause a induced current, but in the opposite direction to the change in that current. And it's going to have the effect of trying to cancel out that change. Another really good way of thinking about it is, if this was a water pipe instead of a wire carrying electrons. Anyone heard water hammering? Anyone seen, like when you turn the tap off, all of a sudden all the pipes in the house go boom? Anyone seen that or heard that before? Okay, so that's water hammering, and it's caused by, if I all of a sudden try and stop that water flowing, that water's moving, it's got momentum, it wants to keep moving, and if I try and stop it, it has to try and make all the pipes move with it. Okay. Similar sort of thing happens here. If I try and stop this current from moving, this magnetic field allows it to have a very similar property to that momentum that the water had, and wants to make the current keep going. Okay? And so that is what causes that that property we call inductance. So it's really opposing rapid changes in the current. Okay? So if I were to have my current all of a sudden drop off like this, so it's stopped, so effectively I flick the switch off, if you like, then this magnetic field here would want to collapse to nothing. But that's a really, really rapid change of magnetic field, which is going to induce a current in the opposite direction. All right? And what you end up having with that is a large voltage across that coil, which we call a back EMF. Okay, I'll explain what that is in a little bit more detail after we've finished with this topic, this section here. So, in a nutshell, inductors don't like having rapidly changing currents. But if you think about what's happening with a sinusoidal signal, the current isn't changing linearly, or it's not dropping off in a hurry, it's changing like this. So if I had a signal like this is my current, which you can think of it, the current and voltage are going to be behaving very similarly, because they're both going through resistive components as well. So the current is going to be a sinusoidal current, and so at the points where it's changing the fastest, the magnetic field here is changing the fastest, and is going to be inducing the bigger current in the opposite direction. So we get a current being induced in the opposite direction. Okay? If I have a high frequency like this compared to a low frequency like that, the current is changing faster here than it is at its fastest point than it is at the low frequency. So the fastest point here is not very much compared to the fastest point here. Okay, so these points are where the current is changing the fastest, and it's much steeper here, and so it's going to be trying to oppose that current change the most here, and that's why at high frequencies the inductor here opposes that current flow more than it does at low frequencies. At low frequencies, the steepness of that curve there, at the steepest, isn't very steep at all compared to this, and so it doesn't oppose it quite as much. Okay, and you can imagine if it's a steady state DC like that, it's not changing at all, so there is no opposition. So for an inductor at very, very low frequencies, it just behaves like a piece of wire. Okay, so it has very, very little opposition to that current flowing. But at very, very high frequencies, we have these steep changes in current here, which the magnetic field changing here tries to stop that, and so it tries to oppose that current flowing through it. And so the reactance of an inductor, which we call XL, is proportional to that frequency. Okay? And in an inductor with inductance L in henries at some frequency in hertz, then the reactance in ohms is going to be 2 times pi times the frequency times the inductance. Okay? And so you can see that if F increases, then the reactance is going to increase. If the inductance increases, the reactance is going to increase. That's different than a capacitor. Remember, the capacitor was 1 over 2 times 1 over, so a capacitive reactance was 1 over 2 pi FC. If F increases, then 1 divided by a bigger number is a smaller number, so the reactance decreases. Okay, so the reactance of a capacitor at high frequencies is pretty much nothing, and at low frequencies is very, very high, whereas that's the opposite for an inductor. So they have the same effect as in they both oppose current depending on their frequency, but whether it's increasing in reactance or decreasing in reactance depends on the frequency, and their opposites affect each other. Okay? So in summary, reactance is due to the changing magnetic field in that coil, which is going to oppose the current being changed. So the direction of the current is going to be opposed by the changing magnetic field, which at very, very high frequencies, that opposition is going to be stronger, and so at high frequencies we have a bigger resistance or opposition to that current flow. Something else with inductive reactance. With capacitive reactance, we saw a change in the phase. So if I had a capacitor and a resistor set up like this, with a sinusoid on the input there, we saw a sinusoid on the output, and depending on the amplitude, depending on the frequency, because that's going to be determined by at high frequencies, this is basically going to be nothing because this has a very, very low reactance at high frequencies. But we also see a phase delay because the current flowing through here is what changes the voltage on that capacitor, and the change in the voltage there is how quickly that, the change in the current here is how quickly that changes the voltage across the capacitor. And so what we see is for a V in, we see that, and the output voltage, okay, so we see a phase delay, so that the peak of the output voltage there is out of phase, so delayed a little bit from the input voltage. Okay, so in our capacitive network, we're seeing there's a change in phase between the input and the output. We get the similar effect. So if I replace this instead with a coil, we get a similar effect in the same way that we see a reactance here, and we're going to see it changing in the output voltage depending on what the frequency is. But we also see a change, so that's the capacitor. We also see a change in the phase, but the change in that phase is in the opposite direction. Okay, so in this case, we're going to see that the voltage on the output leads the input voltage, and that's due to the fact that it's not the voltage changing on here that causes the output voltage to change, it's the changing in current. Okay, so the change in that current there is what causes the output voltage to lead the input voltage. Okay. So the fact that both of these two components, the capacitor and the inductor, have some opposition to current flow, and they change the phase based on the change the phase of the output, but in the opposite sense. The two the capacitor and the inductor change the phase, but in the opposite sense. That has implications when we think about something that we call impedance. Impedance is the opposition to the current flow, but it's the combined effect of the opposition to the current flow of all of the reactive components. So if we have any inductors or any capacitors, it's a combined effect of all of the inductance or the reactance caused by that, and any resistance we might have. Okay, and we can't just add them together though. Okay, so impedance is the opposition to current flow due to resistive and reactive components. So when I talked about reactance before, talking pure reactance, so only the components that is due to the frequency. So a capacitor, if an ideal capacitor, would be a purely reactive component. An ideal inductor would be a purely reactive component. In practice, we very rarely get those. So if you have a look at the big inductors you've got, you'll see how it's got DC resistance. It's about 4 ohms. Okay, that's the DC resistance due to the actual wire inside it. Okay, and so as a result, we're going to have a combined effect of that DC resistance, or the resistance that's got nothing to do with frequency, and the reactance due to the coil itself, and the fact that it's all wrapped around a core, iron, and everything else. So the combined effect of those two, the reactance and the resistance, is what we call impedance. Okay? I don't expect that you fully get your heads around this. Those of you who have done any kind of complex numbers in the past, you might recognise some of it, but I'll show it anyway, and you'll see where the formula for calculating impedance comes from. So a really handy way of demonstrating or showing how we add both the elements of the reactance and the resistance is in a plane. Okay, so if we think of this as the resistive direction, so if I had a resistor, I could think of it as being like a line. So if this was 1000 ohms of resistance, then I would draw a line from this origin to that point there along this line here. Okay, so if I didn't know about reactance, it'd just be a number line. Okay, and so the length of this line is my resistance. Okay, if I had a purely reactive component, let's say I've got a capacitor. So if I had an inductor, purely reactive inductor, and it had, let's say, 1000 ohms of inductive reactance, it would sit there, okay? Positive above, and it would have the length of that line from the origin to that point there would be my reactance of that inductor, okay? If I have a inductor in series with a resistor, then in the same way that we would add their reactances or their resistances if they're both resistors, we can add them together, but these are in opposite directions, aren't they? Okay? So, and they're also what we call a vector quantity, meaning that they have magnitude and direction. And if I'm going to add vectors together, you add them top to tail. And so I really need to draw, if I've got the two in series, I draw, this is my R, and this is my XL, add them together, and then from the origin unto the end point, there is my combined effect of adding the resistance to the reactance. Okay? And so this is what we call the impedance. Impedance has the symbol Z. And how would I calculate the length of that line there? Do you remember how to do that? It's a right angle triangle.
Is it y equals mx plus c?
No.
No.
Pythagoras. Alright?
Do the guy.
Yep. Okay, so we could use Pythagoras to calculate the length of this hypotenuse, where that side is length r, whatever r is, and that side is length x, whatever x is. Okay, and so z, and I'm going to say magnitude, so just put two lines there to indicate that I'm just talking about how big it is equal to, and it's the sum of the squares is equal to the square of that side, isn't it? So if I... Okay, so the magnitude of my impedance there, so the length of the line that I would make if I drew it this way, is the sum of the squares of these two sides, and take the square root of that. Okay? So this is Pythagoras. If you don't understand why I've drawn it at 90 degrees to each other, you don't need to. Really, all you need to know is how to calculate the impedance given the reactance. But there's one thing I have to add here. Notice how I've got XL being a plus. If I had a capacitive reactance circuit, so if I had a different circuit that was a capacitor and a resistor, that would be my capacitive reactance, and it's negative, okay? Remember how before I was saying that the phase difference between a capacitive reactance and an inductive reactance was different, though one was leading and one was lagging? That's why one is positive up this way and the other is negative down this way, okay? And so if you have both of them together, then they can actually cancel each other out. If I just had a capacitor and a resistor, so let's say I've got the same resistor, but I've got a capacitor now, I do the same thing again. It doesn't actually matter which order you add them in, so I can add the resistor after the capacitor, do it the same way. Then that's going to be my impedance here is simply the sum of the squares of the reactance and the resistance. Okay. Remember I was saying that these are vector quantities, so you have to add them top to tail. If I had let's say I have a resistor and a capacitor and an inductor all together, so a circuit like this. Okay, to find the total impedance of all of these things together, I can say that's an equivalent circuit to that. Alright, so this is how we might show it. Just draw it as a resistor, but you label it Z instead of R to indicate it is an impedance, not a resistance. Okay, so I can replace these C, L and R with a equivalent resistance, or equivalent impedance, sorry, like that. And the way I would do it is I would find, so that's XL in there, and there's R, and there's XC. So in the same way as before, you draw the vectors head to tail. So I'm going up by XL, across by R, and then down by XC. Alright? Well, it doesn't actually matter which order I do it in. So if I did the XC next, well, that would just go from here down to here, wouldn't it? Okay? And that difference there is just going to be XL minus XC. Okay? So the combined reactance of the capacitor and the inductor is simply the difference between them. Okay? So XL minus XC is the combined reactance. Okay? And when we, so we can say that this is just X. So when we just talk about the total reactance, we don't necessarily need to refer to it as being capacitive or inductive because it's combined. So you can refer to it as just being X, the reactance. So that reactance there is simply the difference between the inductive reactance and the capacitive reactance. And it doesn't matter which order you do it in when you're calculating the impedance, because you're squaring it. And so if you do it in the other way around, if you do XC minus XL, you get a negative number, but if you square that, you get a positive number anyway. Okay? And so, so if you do it the wrong way around, you'll still get the same answer. Okay. And so yeah, if I calculate my reactance here, that's simply the line from the origin to the end point of my three vectors, and I get my total impedance. Okay? So let's actually do a couple of examples. If I had an example where I've got, guys, just keep it down please. If I have an example where I've got a resistor that's 120 ohms and a capacitor that at the frequency I'm talking about has a reactance of 400 ohms, I want to find the equivalent impedance between that. And so I calculate it. So I'm just going to talk about the magnitude. And it's the R squared plus the... so the combined impedance, the magnitude of the impedance, is the sum of the squares of the resistance and the reactance. I'll take the square root of that. And in this case I get 417.6 ohms. Okay. So the impedance of this circuit is going to be just a little bit higher than the reactance, but it's also going to be some phase delay. We can actually calculate that phase angle, but we don't need to for this course. Okay. You calculate it the same way as if you were calculating those vectors. You can actually, the same way, use trigonometry to calculate the angle. Okay, so if I had a resistor and a capacitor, I've been given the capacitor's reactance, so I can calculate, and the resistor's resistance, so I can calculate the impedance. Okay, so now I don't have the impedance, or the reactance or the resistance. I've got the resistance and the capacitance, and my input signal here is 1 kilohertz. What do I need to find now? What do I need to calculate? The reactance of that capacitor. Okay? So XC is 1 over 2 pi FC, which in this case is only 15.9 ohms. Okay? So 15.9 ohms is the reactance of that. Now to find the impedance, I square it plus okay, so the reactance of this capacitor doesn't really have much effect on the total impedance. It's only 0.6 of an ohm. Okay, so it's pretty small. So the impedance here is going to be pretty much the same as whatever the resistor is. If I did the same at a different resistor or a different capacitor, I would see a different effect. Okay? So a resonance circuit would look something like this. So let's say that's only a small resistor of 10 ohms. We've got, let's make it one of our big inductors, 0.5 henries and 1 microfarad. And we're going to have a signal here that's 620 volts. Okay, So what we need to do is find the inductive reactance, the capacitive reactance. So the inductive reactance is 2 times pi times FL. And the capacitive reactance is 1 over 2 pi FC. Calculate those. Okay. And so now what I need to do to calculate the impedance of my total impedance here is I need to find X, which is XL minus XC. Okay, so 1,691 ohms. And my impedance so the resistor here plays very little role at this frequency to the total impedance because, well, this inductive reactance is huge compared to everything else. Okay. One thing before we wrap it up, just quickly, what we will see if I have a resistive component here, the resistive component is always going to be the 10 ohms along in the real plane, the resistive plane. The reactive component is going to change depending on the frequency. So as I scale through the frequencies, what I see is at this frequency, which is reasonably high for this inductor, at high frequencies we've got a large inductive reactance, so it's going to be up here somewhere. And the capacitive reactance is not going to be very affected by it. At low frequencies, the capacitive reactance is going to dominate, and that's going to be down here somewhere. Okay? And so what I would see is at very, very high frequencies, I would see my reactance is being up here somewhere. And so my impedance will be up here somewhere. Okay, so the length of that is going to be quite large. At low frequencies, I see my impedance is down here somewhere, so my capacitive reactance dominates at low frequencies. And so my impedance is quite long, quite large, down this way. But at some point, it's got to get from here down to here as I go down the frequencies. And at one frequency, the capacitive reactance is going to be equal to the inductive reactance and cancel each other out. Remember that the reactance, the sum of the reactances is XL minus XC, and if XL is equal to XC, then the total reactance is 0. And so at some frequency, we have no total reactance. Okay, so the impedance is simply whatever the resistance value is, and that's what we call the resonant frequency. So that is the frequency where the impedance is lowest in that circuit.